Hey, good afternoon, everyone, and welcome to today's webinar on how to buy a quantum computer. Today, we will take you through LRZ's journey in collaboration with IQM, and we'll share firsthand insights on what it really takes to acquire a quantum computer. So everything starting with the evaluation till the practical considerations and procurement and eventually deployment. So our speakers are going to give you a behind-the-scenes look at the lessons that they learned and the challenges that they faced and the strategies that made this project possible. So whether you're curious on the technical side or decision-making process, etc., you will walk away with concrete and practical knowledge that goes beyond theory. So without further ado, I will hand it over to Silvia Bartel de Vedenthal. She is Chief Commercial Officer at IQM Quantum Computers. And she's going to talk about IQM's journey to being the commercial leader in quantum computers. So, Silvia, over to you.
Thank you very much, Rubika. I'm going to share my screen now. I think you should be able to see my screen by now. So hello, everyone. I'm Silvia Bartel de Weidenthal. I'm Chief Commercial Officer at IQM, and I have great pleasure to present the company to you together with my client and with my colleague. We will talk a little bit about practical knowledge on how to buy a quantum computer. So maybe a couple of words about IQM. Our goal and mission is to build world-leading quantum computers for the well-being of humankind and now and for the future. It is super important and every word matters for us. And I just wanted to highlight that we operate in dual usage technologies, and it's super important that we build something that builds research, businesses, education, and creates excellent, well-paid jobs for every country that we go to. We have right now 314 employees at IQM. Most of our employees, especially on the tech side, are the PhDs. We have 132 of them. We just accomplished the largest Series B in Europe with $600 million a couple of months ago. And we have built fully operating 30 systems. Some of them are with our customers, 19 have been sold. The rest are for our cloud and our R&D stations in our 2 locations in Munich and in Espoo. We were founded as a spin-off of Aalto University in Finland in 2018, and we have over 50 nationalities. It really takes more than 50 nationalities to build a working, fully functioning quantum computer. Our current development is 150 qubit chip, and we will be offering it in 2 different versions. We also have more than 10,000 cloud users today, which we are very proud of because that was our goal to educate as well as to have a community of developers on the cloud. And as I mentioned before, we sell on-premise and quantum computers and cloud. We have 19 different locations for our quantum computers already, and we sell what the industry calls the full stack quantum computers, which means you get everything from the beginning until the end. And it's a fully open, transparent system, which you can use as a test bed, which you can use and see your FPGA access, you can see how your circuits are running, and so on and so forth. The main countries where our machines, the flagship machines, the big machines are operating are Germany, Finland, Italy, and the USA. But we also have smaller machines in most of the European countries, in Italy, in Poland, in France, in one more country will come from Europe very soon, will be announced, I hope, before Christmas. But also we sold and have our machines in Taiwan, in South Korea. So that gives us a fantastic feedback, which is very, very important because all of these prestigious clients are actually operating and giving us feedback every single day. And that makes us work harder because this actually helps us implement this feedback, whether it is on software stack or whether it is on the hardware or chip. That's something absolutely critical. We also work with several partners globally, We have partners for technology as well as for the reselling, and that's something we are very, very proud of. So the next machine that is going to be shipped to Finland is 300 qubit machine that will be shipped in 2027. Next year, VTT, that's the National Laboratory of Finland, National Lab, is going to get 150 qubit machine, and that's going to be then upgraded to 300. It's really important because we have a system that actually you can upgrade effectively from 5 qubits all the way to 300. And why are we different and what is critical for us? We are different because we work with ecosystems. So as you can see here, our offices were first in Finland and in Germany. And once we had the first machines on the ground, we were able to work with the local ecosystem, with researchers, with governments, with local governments, with institutions, with universities, in creating the local suppliers for us, local partners. And actually one of them you will have a pleasure to hear from today, from the Munich Quantum Valley and from Munich Quantum Software Company, where actually we are buying our software. So it is really important that we don't just sell a quantum computer, but we can increase the whole ecosystem. It is something that we use for the future because, as you know, there is very limited talent pool in quantum computing globally. And that is on us to educate young researchers and new researchers and new students to come to quantum, so we can also hire them to our locations globally. I just wanted to highlight one more point here, that this allowed us actually to be the global leader. We have sold more quantum computers on the planet than any other competitor. And in the last 18 months, that gave us unquestioned leadership in volume share, according to Quantum Insider. So we are very, very proud of this. And that gives us, again, more and more feedback. Hopefully, we will have absolutely that feedback coming to us every single day so we can build better and for the future, as I mentioned in the mission, for the better world as we are shipping. It is, again, very, very important for the local economies because according to whether it is McKinsey, Quantum Insider, or other consulting agencies, the category is growing very, very fast, and it has not only the impact on the quantum as the industry, as the vertical, but also on the sister industries and impact on the total economies. So the growth is absolutely super fast. And with the bigger machines, with more error correction, we are expecting quantum advantage to happen in the next 5 to 10 years. So that will be actually the biggest impact probably on the economic growth and value for the end customers, such as enterprises and so on. So that's really important that we actually implement feedback so we can have our roadmap accelerated from the foundation stage, which we assume is ending, to the quantum utility and quantum advantage, whether it is through applications and algorithms, whether it is through hardware production and tight integration, software that we are developing, or development of the chips. As you probably know, we have announced Holocene with 150 qubit error corrected demonstrators. So that's something that is very critical on the way towards accelerating this roadmap. I'm going to very quickly mention the sovereignty of the company. So we have our chip fabrication in Espoo. We are working on more developments there. And we have our own assembly line. We have a data center in Munich, and we are developing with our European roots to the global, to capture the global talent and the global opportunities. And as I mentioned, whatever we are creating, it is super important that we get the feedback at every stage of our machine. Whether it is the fabrication, whether it is the chip production, whether it is the integration system, as well as software, cloud applications that we are working with customers or partners on, or any other part of error correction. I just wanted to mention, for those who don't know us very well, we are part of the superconducting modality together with the key leaders on the planet. And as you know, the Nobel Prize in Physics this year was also given to the scientist in this category. So we are very, very happy that we are working in this part, and we believe we are quite bullish on the growth of superconducting in the future and scalability of this. And that leads me to very quickly what I mentioned before, which is our latest baby. So that's the Halocene. It's a co-creation project, really, 150 qubit with co-created concept with customers or with our partners with error-corrected qubits. And that we see as a huge leap towards commercialization and towards the next steps of what I call in business use for quantum computers for enterprises. We also have Radiance, which is standing in the biggest HPC centers in Germany, in Italy, in US, in Finland. We sell 20, 54, and 150 qubit machines. They are all upgradable. So you can see them, you can notice them, you can work with them already, and you can actually go to, and I think Jorge will talk just after me. He is the person who can work on this machine in LRZ and see it with his own eyes. We also have the Spark for universities where you are starting your journey. So this is literally the lab in a box. We sell it for less than 1 million euro, and actually that's something that students can build and actually develop as they are learning, whether it is engineering or computer science or any other functions at universities. And last but not the least, you can obviously join our Resonance Cloud and see how your circuits are going. You have FPGA access, full transparency, and you have also half an hour free trial. And that's it from me, and I wanted to give the floor to Jorge. Thank you very, very much.
Thank you, Sylvia, for the inspiring and insightful presentation. And to welcome the next speaker, I would like to give the floor to Dr. Jorge Cavaria. He's the lead for Quantum Integration Software Group at the Leibniz Supercomputing Center. And Jorge, the floor is yours.
Thank you very much for the kind introduction, Rebecca. I imagine you can see my slides. And thank you also for the kind invitation. I would also like to thank everyone for attending the talk. And indeed, my name is Jorge. I work at the Leibniz Supercomputing Center. But I also wanted to mention that I am a member of the Munich Quantum Body. And the topic of today's webinar is on how to buy a quantum computer. So I think it's fair to say that in this case, I'm sort of representing the buyer in this transaction. So what I'm going to do is to try to give you the buyer's perspective during this integration. I will focus my talk on the Leibniz Supercomputing Center because that's a place where we keep the system. And I will start by telling you a little bit about LRZ. Then I will tell you why we even started thinking about quantum computing in the first place. Then I will tell you about a couple of challenges we needed to, some challenges we faced and the solutions we proposed and implemented for addressing those challenges. And I will also about a couple of interesting use cases we're already supporting after integrating the system by IQM. So let's start with the LRZ. The LRZ is a major high-performance computing center that provides multiple types of services. It provides, for example, IT services to Munich universities. This benefits multiple people, many people, more than 120,000 students, 27,000 employees, and around 1,900 professors. One of the things we maintain is the so-called Munich Scientific Network, which provides high-speed internet connection via more than 7,000 access points. So basically what I'm saying is, if you're ever in the Munich area, in academic grounds, and you're connected to the Wi-Fi maybe at your room and you send an email, we will most likely be the ones dispatching that email of yours. Besides that, we also provide, of course, IT solutions for science. LRZ hosts advanced HPC, virtual reality, now quantum computing and AI programs. So now I guess it's fair to address the question like, why did we even care about quantum computing in the first place? So I guess maybe a sort of cynical answer is that we, and when I say we, I'm not talking particularly about LRZ, but HPC centers in general, we sort of want to stay technologically relevant, right? And the reason is that it is expected from us, actually, to have this sort of early exploration of emerging technologies. So it sort of fits naturally with our mission, which is, delivering this cutting edge computational capability to engineering and many fields of science and even industry. On top of that, supercomputing centers continuously integrate specialized accelerators, like, for example, GPUs, which is how we see quantum computers. For us, a quantum computer is another type of accelerator, or QPU, if you will. So now the question is, what can QPUs do that classical computers cannot do, or non-quantum computers can do? Like in the same, I'm putting in the same bag supercomputers, GPUs, and the rest, sort of Turing machine kind of system. So in that case, there are many problems that classical computers cannot address. They cannot be solved, or they can be solved, but it takes potentially an infinite amount of time. In that set of problems that you cannot solve with classical computers, you have an admittedly much narrower, a smaller set of problems that can be solved actually by quantum computers more efficiently, many orders of magnitude more efficiently than a classical computer. Yes, it is small, but I think the problems that you can actually address are quite interesting and important, not only for actually many fields in science, but I think they help humanity in general. So, for example, in the slide, I'm showing the traveling salesperson problem. Guessing most of you are familiar with it. It's you have a set of cities, and they're connected via some roads, and then you have either one or multiple objectives. For example, reducing the time it takes to travel from one city to another. Two arbitrary cities. You have that objective. You have multiple constraints, and then you're trying to find an optimal solution for this. The problem with classical computers is that the time it takes to find a solution will grow exponentially with regard to the number of cities, right? So it's not scaling, let's say, nicely. It just explodes, right? And it happens that quantum computers can address these sort of problems. They are very efficient for these kind of things. They have these unique superpowers of superposition and entanglement, which, I mean, it makes me smile, sounds kind of funny, but it's true, right? So if you have a quantum system that you're trying to simulate, I think there is nothing better than a computer that follows, the principles and the laws of quantum mechanics. So what I'm saying is, if you're trying to simulate the dynamics between multiple atoms, molecules, whatever you're trying to discover a new drug, I guess quantum computing makes sense. Quantum computing. So quantum computing is awesome, but classical computing is also great. You can achieve many interesting things with classical computers. You have general purpose computing. It doesn't matter if it takes an infinite amount of time to solve, you can throw the program at it. It doesn't matter. But then you have, again, a set of problems that are, they fit better with the supercomputing, let's call it paradigm. There are some problems that require, or it's much better to address if you massively parallelize or if you are dealing with big data and those kind of things. Supercomputers can help you in that regard. Then another thing is, I could dare to argue, to some extent at least, that quantum computers are currently not standalone systems. So for example, most of the practical algorithms require a hybrid quantum classical loop, like for example VQE, QAOA, and those kind of things. I'm not an expert on any of those, but it's one of those are like the algorithms that we are requested to keep our software performant and tailor for those kind of algorithms. So it's telling us something. And then for those, you have all this parameter handling and optimization and so on. Then you have compilation, just-in-time compilation. You get a circuit and you need to make it compliant with the target architecture. Then you have to deal with all, mapping to the topology of the superconducting system, decomposing everything to the native gate set. What else? Reducing the depth of the circuit to be within coherence times and so on and so forth. So only with those sentences, I already covered a few NP-complete problems, right? So you have to use some heuristics, and you need what we're expecting is having to utilize supercomputers to deal with this sort of compilation. When we reach the millions of qubits. Right now, you can still compile a circuit using a laptop, but we don't know what is going to happen in the future. We don't know how well this will scale up. So we just are trying to be ready in that regard. Then we have post-processing, making meaning of the results, handling error, correcting codes, and the list just goes on, right? So for those problems, I guess we can agree we really need HPC resources, like fast, low latency, large scale, classical resources that HPC centers already provide. So that's why we are sandwiching quantum computing with supercomputing, and we are looking for this, what we call an HPC-QC integration. So the plot on the left is basically showing what I was telling you before. The horizontal is the problem size. I mentioned cities. I was also talking about qubits. And then the vertical is the problem, the time it takes to reach a solution to that problem. So as you can see with the blue curve representing the classical computers, this just explodes. It's not scaling gracefully. But quantum computing has this really nice straight line. And after you intersect on the horizontal, everything that was on top of this orange curve is what we call the quantum advantage, when we reach quantum advantage. And keeping that in mind, and keeping in mind also things like how cheap it is to maintain a system, like when you compare with a supercomputer, which is in the megawatt kind of ballpark, um, quantum accelerators are in an order of magnitude lower than that. So considering all of these benefits and what I was telling you before, and the whole thing with the AI going on, we are now getting closer to what I was saying before, this HPC integration, this quantum supercomputing. Um, so, um, Sylvia was already mentioning resonance, which is one way to see the problem, submitting one quantum job directly to a quantum computer. That's entirely valid. It's fine, it works. But then you have to think what happens when you bring HPC into the game. Please don't worry about trying to understand all the text. I made it entirely on purpose like this. I'm just trying to show the sort of complexity we have to deal in this kind of like system, the HPC system. So super quickly, let's imagine you have a big job that you need split into multiple pieces. You will allocate resources and whatnot for each one of these pieces. And then those pieces will start spitting out, the quantum part of the problem, the quantum kernel. So now you have potentially hundreds, if not thousands, of quantum circuits you need. If you start dealing with batches, for example, then you have this many quantum circuits you need to compile, to make compliant with the device. But then what happens if you actually have a quantum fleet, like Atalar said, multiple quantum devices, different technologies, now try to address this issue. And then if you bring into the question remote submission that requires no HPC resources, which in our case we funnel directly to the second level of the scheduling, then you see what I'm trying to show in this one slide, like this two-level scheduling kind of thing. So I'm actually trying to make a point, which is that we need to operate within the existing HPC framework, right? So HPC centers enable already fair shared access to expensive hardware. Quantum devices are actually costly, and they are also scarce. And HPC centers have already established solutions for these problems. So we have allocation models, fair share schedulers, user support teams, security and access policies, and so on. So let me walk you super quickly on how we consume and handle that job. Everything starts from the top left side. The user, a human or an automated tool, submits a job to our infrastructure. Then we take that job. Like I said, we split it into multiple chunks. Each one of those chunks will reach a compute node with access to quantum acceleration. We compile those pieces. Then we offload everything to the control electronics. All these abstractions, all these quantum gates and stuff get translated into pulses. Those pulses get fired into the chip. Then we measure the results, create some statistical results out of that. And then we have to ask if we have reached a sort of stop condition. If we haven't, then you start iterating. So in this case, we are talking about a hybrid algorithm like BQE kind of thing. And when you finally reach the stop condition, then you can forward the results back to the end user. So it's more or less how we handle things. If you want to know more, please check this out. We just published the MQSS paper. There we are introducing the components of the MQSS. We're trying to describe the details as much as we can. But of course, we couldn't cover every single detail. Any questions you may have, please feel free to reach out. You will find our emails right there, and we can try to answer all of your questions, or maybe contribute and collaborate. This is my very last slide. I will leave it there. I just wanted to show you 3 different resources. I think very interesting use cases that we're already supporting using the system from IQM. Actually, some of the co-authors, I'm happy to say they are my colleagues. in the middle, but I mean, there is also this other paper by IQM. Please do yourself a favor and check them out. I think they are very interesting. And yes, this is my last slide. Thank you very much.
Thank you, Jorge. And just for everyone in the audience, all these papers are under the resources tab, so you can access these papers from there. And thank you, Jorge. So for the next part of our agenda, I'd like to invite Eric Mansfield, who is the Senior Product Manager at IQM, and he's going to share a practical guide and his experience.
The archive link is here at the bottom. And really, our goal with this paper was to just fill in the knowledge gap about what it takes to actually install a quantum computer in an HPC center, and to share kind of the nuts and bolts and some lessons learned, things that went well, things that didn't go well, and why we think putting quantum into data centers and HPC centers is more practical today than what many people think. So to start, I would like to show a photo of our IQM Radiance 20 as it looks today. As you see, the Radiance 20 is streamlined. It has a form factor that's very close to that of HPC nodes that you see in top tier supercomputers like Frontier or Jupyter. Now, the thing though, I think it's really important to understand is that a quantum computer is not a classical HPC node. So here on this picture on the right, this is an exploded view of one of our test systems. You'll find even more detail about this system in the paper. It's linked below on the left. But starting from the left-hand side, in this image, you can see that we start with the measurement rack, which contains a server, which is the kind of the brains of the entire operation that orchestrates running the quantum computer. We move up a little bit further in the rack. We see we have microwave control electronics that send microwave pulses into the cryostat, more commonly known as the chandelier, which is gold when it's opened, but in this case, it's just a white tube. These signals go into the white tube. They go down. They get cooled down to 10 millikelvin, where the QPU itself is located, and then the signals are taken back out from the cryostat and brought back out to the measurement rack, where they are read. And then you're probably looking at this and you're looking on the right-hand side and you're saying, I don't recognize a lot of these things from an HPC node because I'm not using helium compressors. I don't have cryogenic gases. And I also don't have this large drap tubing that's used to dampen kind of the noise that's coming out of the pulse tubes to cool the system. So all of these components seem a little different and a little scary at first sight. But they're all, important, and they're all things that can work in HPC. So let's just kind of dive inside. So remember, we had the white cylinder, the cryostat. We take off the cap. We have the gold cold finger or chandelier, that's more commonly known as. And you can see in the middle picture, we're zooming in on the wiring, and in the middle, on the kind of in the bottom, you can also see that there is something called a dilution refrigerator, which looks like these series of stacked circles. And this is where we're getting the cooling that allows us to achieve temperatures that are close to absolute zero. But one thing I think you could take away here is there are a lot of wirings. And all of these wires have opportunities to introduce noise into the system. And it happens when there's thermal expansion, when the building itself shakes, when you play very loud music nearby. And so when we're installing the quantum computer in the facility, it's very important that we're minimizing the potential for these vibrations. And then if we zoom in all the way on our QPU, and this is just a little peek of a 5-qubit QPU, you can see that the features themselves are quite large because we're using microwaves. Everything is millimeter scale, but the signals themselves are very weak. So the actual like amps that are in a single qubit are around 1 to 2 microamps. So this is a very faint signal, and this is why it's so important that this signal itself is protected from the outside environment, which is why if you go back on the left and the bottom, you'll see that there's this silver metal can. That's the first level of shielding that goes around the QPU. And then we put a bunch of different layers around the system, much like a Russian nesting doll, in order to lower the background E&M environment as much as possible. So now that I've explained that generally, though, I would like to give you some actual hard numbers to use when assessing if you can install a quantum computer in your facility. So these DC and AC magnetic field measurements are made by putting a 3-axis flux gate sensor So we take the sensor, we stick it on a tripod, in exact the location the QPU will be located in the room, and we collect 25 hours of environmental data to see if there's anything happening in the room that'll make it difficult or create interference and noise with the quantum computer. Now, some things that we found in the past are problematic are, for example, if you have high voltage DC lines to power your HPC nodes, if you have pumps that have very noisy electrical characteristics, or if you have old school fluorescent lighting, all these things could create magnetic fields that could create noise in the system. Now, I also talked a little bit about vibrations. So with vibrations, the good news about superconducting qubits is we do not need a giant floor-sized vibrational isolator. But experience has shown us that we should not be, for example, directly next to a bus stop, a train station, or any of these things that create a lot of large vibration. And typically, customers find it easiest to place our quantum computers directly on the concrete floor or the false floor of the facility at ground level. Now, sound pressure is an interesting one. So we're specifying less than 80 dB, which is, I would say it's about as loud as it is when you go to a bar on a Friday night, everyone's having a good time. But if you can go over that, for example, some of our colleagues in Helsinki, they love Finnish death metal, and sometimes they do blast it, and we can see noise in the signals when this happens. So we recommend that when you're working with the system, that you wear headphones, so you're not blasting loud Finnish death metal. And then lastly, temperature-wise, we want to try to minimize how much temperature excursion we have in any 24-hour period, because there's a lot of these signal wires that are going in and out of the system, which are coated with Teflon. And if anyone remembers about the famous PTFE knee, you can cause some subtle phase shifts in the signals that are being extracted if we're going through different temperature transients throughout the day on the quantum computer. And lastly, we want to avoid condensing humidity for both because it's bad for the room temperature of electronics, and because we don't want to condense water on the cryostat when we open it and it's still cold. So when we worked with LRZ to install the quantum computer at the facility, it started by finding 3 different spaces. Now, these 3 different spaces were assessed to see which one were best for these background noise environmental characteristics, and then also for access. So you see some pictures here. One of the things you will see is that the quantum computer is definitely taller than an HPC node. Our system today is 290 centimeters tall, and it does require a floor load-bearing capacity of about 1,000 kilograms per square meter, which is in 4-point loads, just a frame that supports the white cryostat. One thing that is very encouraging, though, is that we can take the entire radiance apart, and we can physically move everything through doorways that are no wider than 90 centimeters and 220 centimeters tall. So that means that we can fit through the majority of doors, elevators, walkways, ramps, loading docks that you find already today in HPC centers. So you don't have to cut any holes through the walls. You don't have to bring a crane in and try to put it in through the roof. This is all possible today. And some of these components which are heavy, so for example, here in the center image, you'll see these are pulse tube generators, which allow us to achieve those ultra low 10 millikelvin temperatures. These can, for example, be put in the drop floors. They can also be put in their own separate room if you want to lower the acoustic noise. But everything is very doable and customizable for the site. And some become very practical. So our quantum computers use input water with a temperature between 20 and 25 C. And most HPC centers we've spoken to have either 2 or 3 different temperature of water, where this 20 to 25 C is one of the lower temperature loops, and there's usually a 30 to 45 C loop as well for some applications that are less sensitive. Also, we use barely any power compared to HPC racks. So I think you notice some of the latest generation Cray racks are using somewhere between 300 and 400 kilowatts. And Meta is in the process of building a 1 megawatt rack. And we're coming in at less than 30 kilowatts, with the majority of that power being used for the cryogenic cooling of the system. And that also, what's good is because it's mostly going for the cryogenic cooling, as we scale up, as we add more control electronics, as we add more infrastructure, we do not significantly increase our power consumption. And lastly, we need to add a small compressed air compressor just to actuate some of these pneumatic control valves in the gas handling system, but nothing exotic. So after the system's been brought in, there is a commissioning process that takes a few weeks where the system is cooled down. The QPU is tuned to its best calibration, and this is based on what we've already achieved at our facility in Helsinki when we have taken the chip down and tuned it up. And also we then perform a suite of benchmarks, and we do an acceptance with the customer based on these benchmarking results. So I think one thing that's really worth highlighting about quantum computers, and this is true across all the modalities, is that a quantum computer is not a GPU. So when GPUs are manufactured, they're tested, their clock frequencies are determined in the factory, everything is tuned, and the system is calibrated essentially for life. But quantum computers are dynamic. There's a lot of different parameters that need to be adjusted and shifted in order to find the optimal calibration state. So this is something you need to think about when you're planning your workload in your HPC center, which is that, for example, at LRZ, our system takes about 40 minutes to do a rough calibration, followed by an additional 60 minutes to perform a full suite of benchmarks to ensure that the system is ready to go and has the performance that we want for daily use. But I think what's nice here, though, is that even though that does sound like a long time, I have heard that other modalities do require longer times to tune, and often human intervention is needed, whereas our system is completely run automatically by a cron job without any human intervention. In fact, day to day, superconducting qubits are essentially lights off. So there are no resident engineers being required in the facility. Everything can be handled by our team through remote SSH access to manage the system. And then once a week, somebody needs to go in and spend about 5-10 minutes adding 10 liters of liquid nitrogen into the cryogenic cooling system. And that's just used to kind of flush out any other residual gases that condense into the cooling loop, or so that we always have nitrogen in our loop, and we don't have nitrogen plus a partial pressure of argon plus partial pressure of CO2, et cetera, et cetera. And kind of to back up that claim about not having human touch, we're showing here 150 days of operational data from Garnet, which is one of our cloud-based systems. And you'll see that there have been no outages, that both our 25th and 50th percentile qubit fidelity values remain very stable during the entire time. And you don't have to just believe me. Researchers at the TUM University and LRZ recently published this paper here with 270 days of data. This is complete open kimono. We had no role in creating it. You'll also be able to read this paper, and you can also see what happens, for example, when the system needs to be warmed up to do maintenance on some of the cryogenic cooling. And speaking about that and figuring out what it takes to integrate a quantum computer into a data center, one of the things that LRZ has really been leading with is something called the telemetry project. So they've installed 508 environmental sensors around the quantum computer. They're also collecting data from the sensors that are already built into our system in order to determine what affects having the optimal calibration state, the optimal GHZ, and how we can make sure that we're reducing the background effect of environmental factors on the system. So I do encourage you to read this paper. And the one other thing I would say, as we get towards the close, is that one thing that's made LRZ successful, as Jorge was showing with those 3 papers previously, is that LRZ had an early user onboarding phase, where users either came with a deep quantum background and they were new to HPC, or they had deep HPC background. They remembered the experience of getting to touch the first GPU in 2012, 2013, and now they wanted to come and learn how to add quantum into their workflow, so they can add this novel computational accelerator to their work. So, in order to make this possible, IQM first trained our LRZ solution architects, And then LRZ, which has a long history of training its users, had hosted multiple trainings, had live feedback and Q&A sessions. And by doing this, they were all able to create this community around Bavaria that's able to do this high impact research with quantum computers. So in brief, I wanted to say that quantum computers have a stricter but manageable facility requirements, that calibration is part of what makes a quantum computer different from a classical HPC node, but this is something that is automated and manageable, and that structural onboarding and training results in success. And if you want to learn even more, I highly recommend you do read the paper that Jorge and I wrote. It has even more details about everything we want to know about physical installation, how to get started, and where to go. Thank you.
Okay, thank you, Eric. So in the next part of the agenda, we'll have a discussion with all the panelists and answer some of the questions in the Q&A, but also some that have been submitted earlier. So let's start. Just a minute.
Okay.
Eric, can you stop sharing? Okay. All right.
About the questions, if I
Yes.
may. I was already typing an answer for you. Hold on. Yes, I'm sorry. I'm not sure if I can say your name right as Har. I was typing an answer for you already, but I think it's better if I just do it like this because then I can also let Eric share the experience from the IQM side. But at least from our side, one of the biggest challenges I think we faced is when you actually put two different modalities next to each other. For example, neutral atom systems have this really big magnet inside, and putting them next to an ion trap can be a problem. We have noticed, for example, the subway passing next to our building. I think it's 300 meters or something. We have also noticed spikes in the electromagnetic field whenever the lift is used in this ion trap system. So putting modalities next to each other is one of those challenges you really need to think through.
Yeah, and I think also when it comes to environmental concerns, it's also important to segment out, HPC centers from research organizations to, for example, and then the kind of this full spectrum of data centers from people that are doing high performance, high frequency trading where they have very tight environmental regulations, all the way down to I just pay by the tile and there's nothing in the facility. So we find really that people who are more sophisticated generally already have these tighter environmental requirements met, and they're able to satisfy installing the system. One thing that some people do find is that for example, that their water cooling loop already is a little bit warmer than what we would like it to be for an input temperature, and so they'll add a sidecar to the water cooling just to drop the temperature by about 5 degrees Celsius.
Okay, so I think the next question we could take, this is for anyone who wants to answer it. What would be the total cost of ownership, or what factors need to be considered in the total cost of ownership to purchase a quantum computing solution?
I'm guessing that was targeted to me. So I guess one of the biggest things, at least at the very beginning, you have to consider is that, again, the type of systems you will have, the space you need, because, for example, with the magnet example I was just giving, either you put it far away from the other or you put a cover around it, right? So you need to check what is the status of your lab or whatever environment you are planning to put the system in, and then check what are the next things you need to consider. Because some systems require to be like within this very specific temperature range, and you need to check vibration and stuff like this. But I will let Eric address the specifics about
Yeah,
actual
I think
systems.
when you look at total cost of ownership, first of all, there are very few consumables used in the life of the system, and we're building on the cryostat just over my shoulder is built on technology that's been around for about 60 years. So these systems can be run pretty much indefinitely, so long as you continue to replace seals, gaskets. You do the regular maintenance every 6 months. So we see that there's fairly low costs. If issues occur, it's almost always with cooling.
Okay, and there's a question, if a client decides to purchase multiple machines, so what are the options and advantages of interconnecting them, and what equipment is required for something like that? So I guess it's for Eric.
I think maybe Jorge wants to talk about QDMI.
I was trying to understand if the question meant interconnecting two computers with each other or independently. For example, we have at LRZ, besides the quantum accelerators, we also have other types of appliances from Evident. Those are classical systems, but they can simulate or emulate other backends. So what we did with the interface specification Eric was mentioning, which you can also find the details in the papers we showed you. With that one interface, the QDMI, Quantum Device Management Interface, or QDMI, you can not only interconnect your software stack with the backends, but also backends with each other, so they can talk between them. I was giving the example of the captive appliance because we're currently using it for multiple things. One of those things is, for example, again, emulating another backend. So you can get, or the captive appliance can get a circuit plus the name of the backend it has to emulate, and then the QDMI talk to that backend, fetch the noise model, then start behaving like that backend, and then simulate now the execution of the circuit. We get the results back to the end user, and then the end user can decide to resubmit it or not again to the actual backend and then compare results or whatnot. So that's one possible scenario. If you're talking about distributed quantum computing, then things are, of course, way more complicated. There you need quantum links, quantum memories, and other kinds of things, which we are currently not admittedly looking into. Potentially in the future. But yes, about the other scheme, the other setup, QDMI, I believe, is, at least we have a lot of hope on it.
Okay, the next question is from Sam. He's an industry analyst. Can an organization running a standard data center incorporate a quantum computer as well as a supercomputing center, or will they need to significantly increase their technical assistance, training, support?
So I think this is a really key question. So one of the things that IQM has been doing for over a year now has been working with the Open Compute Project to establish both a checklist and a white paper as a precursor to a standard for retrofitting data centers to hold quantum computers. I think the answer has shown so far is that different modalities require different levels of support. I think superconducting, from what we can see, requires really the least hands-on touch for a system. So in practice, you only really need to train the people in the facility to add a little liquid nitrogen every week to the system. And with the future designs of Radiance and Halocene, we are planning to remove the nitrogen. And if we can do this, then it should be hands-off, hopefully for up to 5 years.
And maybe, Sylvia, what role does IQM's ecosystem play? I mean, you spoke about it briefly. So what role does it play in accelerating customer success with quantum technologies?
Fantastic. Very good question. Thank you for this. So when you have the open ecosystem, the open full stack quantum computer, you can work with different small businesses, with researchers, with developers, and you can actually develop every part of this stack, and you can test it. You have the test bed where you can actually go and test it. So I think Jorge is the best example here, actually, because we are buying now the Munich software company software on our machines, and that was created as a result of the fact that we had those machines in place in Munich. That's one of them. Another one is that, if you look at any cables, any part of the machine, even, the chip holder, we need a lot of suppliers for this. So that's one part on, impact on businesses and so on and so forth. The other part is you can have companies who are, for example, specializing in error correction, or in all sorts of NISQ mitigation and so on and so forth. These are companies which are very, very important for our growth because, as you know, there is still a lot of noise in the category and we have to work with this. So we're not going to be able to hire the next, 200 experts in PhDs in quantum to fix that. We need to, rely on our partners who are doing it. So that's another example. And last but not the least, I really believe I come from business, that if you give a toy to the business people and to the scientists and to the researchers, they will bring things that we cannot think about. You need very diverse thinking to generate growth, progress, and that's where the faster, accelerated growth in category will happen. So I just want to encourage everyone to really try, test, and do the things that our scientists are not doing because they are thinking in a specific way. And that's where I see the growth will happen. If you look at McKinsey's report, the impact on the economies globally is going to be $1 trillion or even more. And again, I don't want to hang on to the numbers of prediction, but we already see that, for example, in Finland, we have 13 startups as a result of this. We only had 2 in 2019. Right now we have 13, and the impact on the economy is such that those startups have over 1 billion euro invested in them. And I will not even dare to calculate what's now in Bavaria, because we just saw 9 startups just in Bavaria region as a result of our machine being on the ground in 2020. And now the investment in those startups is again bigger than 1 billion. So those 2 ecosystems are, I think, the best ones to present as the impact on the economy. And if you look at the companies that were created, it's everything from hardware all the way to software through error correction and algorithms and so on.
Great. And Sylvia, there are 2 more questions. I'm just going to merge them. So for early stage startups who are exploring simulation modeling, etc., and they need a quantum computer, so is there any process that we can help them to fund their first purchase, and how do they begin, I think, and how do we partner with them?
So if these startups are in the European Union, there is a lot of money in EU for smaller businesses and medium businesses to actually either buy the cloud or buy the quantum computer, because that's innovative technologies and you can use a lot of money from the EU. There are also local funds from any country. I know that it's in Italy, it's in Spain, it's in Poland, Germany, Finland, where you can, combine the local budget with the European budget. So that's something that we see with the customers who we are working with. But if you are a small company and you just have to start, then I can offer, our cloud first, because if this is just the beginning, cloud is just more effective. The difference between our cloud and competitive cloud is that you do see your circuits, and our machines are standing in Finland and in Munich, and you can see them, you can touch them. If you are in any of our countries where the machines are already installed, like for example, Oak Ridge National Laboratory in the USA, or in Cineca, or in LRZ, or VTT, you can also reach out to those clients because they have a lot of programs in place to help the local ecosystems. And that's something very powerful. HPC centers have fantastic missions to impact the local economies, but also to help. So I would definitely reach out there. If you go directly on our Resonance crowd, you will get also some credits for free. We are also working on libraries, on different ways of supporting that. We're not ready yet, but that will be changing in the next year to come. We just hired 2 people for it, so you can expect a lot of changes happening there as well.
Great. And Jorge, maybe this is a question for you. Were there any notable surprises for you during this QC installation and setup?
Indeed. I mean, I guess one of the most interesting challenges was the double scheduling approach we follow, because of the reasons I was saying during my presentation. We also have to, like I said, we're talking about just-in-time compilation. We need to make sure the circuits are compliant with the system, which in superconducting systems implies mapping to a specific topology. which again, it's a very big problem, and we are doing a lot of research over there. IQM already provides their solutions, like as a standalone system. But we on the other side, and this is also addressing some of the questions I was already trying to answer in the chat, we are leveraging a LRZ Munich quantum software stack, which has to be, let's say, sort of self-contained. And it also has to deal with these other many technologies we have. It has to be agnostic to the technologies behind, and we have been fortunately being supported by IQM all this long, trying to integrate or interface QMI, as we were just saying. Now it's officially supported by IQM, which is obviously helping us, to address this challenge.
Okay, and Eric, what kind of technical support can IQM provide if somebody were to purchase a quantum computer from us? And what, in terms of diagnosing and resolving any errors that may arise, what is the support level that is offered?
Yeah, so IQM typically provides a 3-level support, where there's a first contact via our support portal, and a response within 24 hours, often even faster, and then it can be escalated to higher and higher levels, with somebody coming on site to fix any issues that are necessary within a few days to a week, depending on if parts need to be replaced. The exact details of support packages are available under NDA.
Okay, and I think there's just time for one last question. So maybe Eric, you can answer this. So what is the most common misconception that customers have that you have heard while buying an on-premise quantum computer?
I think that the biggest one is honestly that it's not possible to buy a working quantum computer today.
Okay, hopefully we change that today after this webinar.
Yeah.
So we're almost out of time. So I want to thank all our panelists. Thank you, Jorge. Thank you, Eric. Thank you, Sylvia, for joining us and sharing your insights. Thank you to everyone who joined from the audience, and we hope to see you again soon for another webinar from IQM. So watch out for our emails, and shortly after this webinar ends, you will receive a survey. So we really appreciate your feedback. So please share your thoughts on this webinar. So thank you very much. Have a great evening ahead and day ahead, and thanks a lot. Thank you.
Thank you.
everyone.
Bye, everyone.